it seems with high probability my talk starts with a definition of graph homomorphisms. So, graph homomorphism, perhaps everyone here would just know what that means, but let me just recap. It's a vertex map from some graph H to another graph G that preserves adjacency, which means whenever you have an edge here, then this is also an edge. Okay, and the graph homomorphism density, Th of G, is the number of homomorphisms from H to G divided by all the possible vertex maps. In other words, it's a probability that a random, uniform random vertex map is an homomorphism. Let me just say.
When you write, make sure it's far away from the
I see some resonance problem. Oh, I see. I'll try. I'll try my best. Yeah, so this is graph homomorphism density, and many statements in external graph theory especially can be rewritten in terms of graph homomorphism density, but let me just this time go just straight into Sidorenko's conjecture rather than just like explaining what this notation means. Yeah, so there's a beautiful conjecture by Sidorenko and also by Erdős and Simonovits in a slightly different form, which states the following. So whenever your H is bipartite, and given any graph G, this simple inequality holds. So it's very simple, just one line inequality with very simple condition. So let me just start with one remark that this H being bipartite is necessary, because if H is non-bipartite, then we can construct a graph G quite easily with positive edge density, but with H density 0. For example, if H being a triangle, then you can just take a complete bipartite graph, and then you have H density 0, but on the other hand, your edge density would be positive, so you can no longer expect this type of inequality to hold. So this bipartiteness is really necessary. And this is a major open problem in external graph theory. Well, there are several reasons I can give you why this is an important problem. Firstly, it's a natural extension of Tran's theorem, or Erdős Simonovits theorem for bipartite graphs, if you know what that means. And it's important. It's also important because it's a strong type of correlation inequality, which means, so look at the right-hand side. So this conjecture essentially states that your number of bipartite H your normalized number of bipartite H is minimized when your graph G is a random graph. And again, in other words, that means if you have some other graph G than a random graph, then you have a larger correlation to have your bipartite graph H that you're in your graph G. So this simple inequality really asks some correlation in what if you just sample some number of vertices in your graph G and you end up with a homomorphic copy of H. So that's, hope that convince you this problem is interesting. So let me just, so what's known? Let me just add a few words about what's known. So Erdős and Simonovits conjectured a slightly different version of this conjecture in 83, and Sidorenko perhaps done it in 91. And the reason why this conjecture is like known as Sidorenko's conjecture is so Erdős and Simonovits conjectured this before Sidorenko did, but Sidorenko's conjectured in a slightly different form, and he added some nice examples. So firstly, Sidorenko proved in early 90s that, let me add one definition, sorry. Here's one definition. So let's say H is a bipartite graph, H is Sidorenko if this holds for any G. This is one definition. So let me just list up the known Sidorenko graphs. Firstly, Sidorenko proved that every three even cycles, all even cycles, and if my H is an so let's just fix a bipartition A union B of H, and three even cycles, and if one side of bipartition has at most 4 vertices, then these graphs are Sidorenko. So this is perhaps the first substantial non-trivial work on this conjecture. And later on, Hamed Hatami in 2010, I think, he proved that hypercube graphs are Sidorenko. But this is slightly unfair to say that Hamed Hatami only proved this, because he proves some strictly stronger property than this property being Sidorenko. So let me just postpone what that is for some minutes. And then David, Jacob, and Benny around the same time proves that if you have a vertex, special vertex V that's adjacent to all the others on the other side, then the graph is Sidorenko. Yes.
Is it known if we increase somehow this exponent?
Yes. Yeah.
So if it was there instead of 100
Mm-hmm.
or
yeah, that's
that
also.
true?
That's
I mean,
also.
is it true for some number? Or
Yeah, that's also a very good question. So, this paper by David, Jacob, and Benny, the title of this paper is Approximate Version of Sidorenko's Conjecture. And the reason why they named the paper so is by adding these edges to make this special vertex exist, they could put something, some bound in terms of the number of edges that they have to add. Yeah, they prove such an approximate version, and hence the name. Yeah, so yeah, that's a very good question. Yeah, and there are some other results on like Ramsey multiplicity questions and so on. Yeah. Yes.
More basic question. Do we allow like edge collapse in graph homomorphism?
Yes. 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 Exactly. So this vertex map is not necessarily one-to-one. It's just a map. Yeah, just a map. And yeah, and hence this normalization makes more sense. Yeah, we don't care about degeneracy. But asymptotically, if your graph tree is dense, which means it has this many edges, then these are asymptotically same. Yeah, so we don't really like terribly worried about these degeneracy issues. Yeah, you can just casually think about some these homomorphic H copies as some real H copies, if you'd like. Yeah, I mean, just for this problem. Yeah, yeah, within this version. Yeah, yeah. Yes. So, sure. Yeah, we talked about this CFS, and later, Joonkyung Lee and Balázs Szegedy, I would say 11 plus, because it's submitted in like 7 years ago, but so far it hasn't appeared, but it's so yeah. So they basically reproved this result and some other results too. Reprove these with some new technique, which they call logarithmic calculus, and that means you apply Jensen's inequality for logarithmic functions like log x or x log x. Right. So, and there are some subsequent work by Joonkyung Kim and Joonkyung Lee and myself in 2000. Not sure about the year, probably 14, 15. Not sure. Yeah. So we extended this result, which we called tree arrangeable graphs. But I'm not going to talk about the details of the definition of these various classes of graphs, but I'll rather focus on methods and how it worked in a very rough sense. So, yeah, this is one of my first papers in this Sidorenko's conjecture, and later Balázs Szegedy, well, it's still plus, and David, Joonkyung Kim, and Joonkyung Lee and myself around the same year, but published it in 16, I think. Yes. Yeah. So these two results are kind of compatible, although written in a slightly different manner. So these results extended this one and perhaps some others, plus others. And what else? And we gave some other approaches too, which I'm gonna talk about in a second. And there's a result by David and myself proving probably published last year. Yeah, last year. Yeah, I should distinguish myself with Jungbo. So, yeah, so proving the reflection graphs are Sidorenko. So I listed up more or less all the results, but let me just go over again with what methods they used. So what Sidorenko used is some sort of Mobius inequality plus some other ideas. Yeah, it's an old paper. So I'm not very sure about the exact method he used, but yeah, he used some basic Hoders inequality and Cauchy-Schwarz inequality and so on. And what Hamed Hatami used is again some Cauchy-Schwarz in a very very delicate way. And what David, Jacob, and Benny used is the dependent random choice method. And for me, dependent random choice itself sounds like this graph. So dependent random choice always always samples some vertex like this and look at its neighbor to embed a smaller graph. Yeah, if you're used to this technique, then you understand what I mean. So yeah, so they use dependent random choice, and Lee and Balázs Szegedi used, as I told you, this Jensen's inequality for logarithmic functions. And we also use this Jensen's inequality. And actually, we've done a little bit more about box products, which I didn't really mention here. So this other approach also includes some box product thing. But this is more like elementary one-to-one correspondence trick. So yeah, as an analytic tool, I'll just skip that box product part. Yes, and if you know these entropy inequalities used in information theory, then you would immediately notice that this Jensen's inequality for logarithmic functions is just that. So when you prove something about these entropies and etc., you just start with applying the Jensen's inequality for logarithmic functions. So it's kind of natural suspicion that one may be able to extend or like rewrite these approaches in terms of entropy. And this is what we and Balázs exactly did. So we used some information theoretical approach. And later, my approach with David is quite different. So this is an extension of Hamed's result, which proves the strictly stronger property, so-called weakly norming property, than being Sidorenko, than the Sidorenko property. And what we used is, again, Cauchy-Schwarz, but in an algebraic way. So this might sound a bit weird, but what we basically did is we encoded the applications of Cauchy-Schwarz inequality for graph counts in terms of some algebraic tools, like using finite reflection groups. And yeah, we expressed such an application in terms of some algebras some group operations in finite reflection groups, and we kept track all these applications up to the like possibly infinite number of applications, and hence done something. So there are various tools and various ideas in all these results, but for these recent results, we use almost all the ideas in these results. So let me just highlight what we use. So firstly, we needed Holder's inequality, but it's slightly different from what Sidorenko used in his paper. So we used Holder's inequality, and we also used dependent random choice. This is a bit cheating because we directly just used this result by David Conlon, which can also be proved by using these logarithmic calculus or entropy inequalities. And what else? And we also used this part. So we used this part. We also used this part. So we used these three tools, and again, this can be reproved by these techniques. And by using all the tools we developed, we proved something new. Right here, or I'll try to write here. So what's the statement? So the statement is as follows. Given my bipartite H on the bipartition A union B, there exists some P, which depends on H, such that my P blow up along A of H is Sidorenko, which means, so here's my H, and I take P copies of B. And
P is the integer?
yes, yeah. No, this is more like the P from LP. Yeah. So, well, in that LP, P doesn't really have to be an integer, but yeah. But there is an integer P, so we take P copies of B, and then we connect these. So we basically take a P vertex-disjoint copies of H, and we glue them along A. So this is my definition of the P blow-up of H on A. And if I do this, so if I blow this graph on one side with a sufficiently large number, then this is Sidorenko. This is a very general statement. So there are various results like this, but the thing is, all the results are kind of explained in terms of some recursive fashion. So, for example, this information theoretic approach gives you some large class of graphs that are Sidorenko, but still, they have to be built with some small pieces like trees, like trees of trees, or you basically glue trees in a tree-like way, and so on. You just iterate, and so on. But on the other hand, this result just gives you, just no matter what bipartite graphs you have. You can just blow up one side, and that's Sidorenko. And another remark is that in external graph theory, this kind of blow up is quite common. For example, any complete bipartite graph is a blow up of a star, say. So K1s, so I messed up some notation. So K1s on the S side, something like this, yeah. And recall that the classical result by Kvari, Schoch, and Turan says that the external number, well, I have to define this, but this is the maximum number of this free maximum number of edges in KST free graphs, n vertex KST free graphs. Yeah. So Kvari-Schoch-Turan theorem gives you this bound, and it's believed that this is tight. It's widely believed that this bound is tight, and it's actually proved for some large t, say bigger than s minus 1 factorial. But people believe that this caveat here for the lower bound, so this implies that this is actually tight. But what people usually believe is this caveat here is just because we don't really understand the lower bound construction for good lower bound construction for KST free graphs. So they do believe that some people, I mean, at least quite a few people, believe that one could relax this caveat up to this optimal point. And if we think about a similar thing would hold for the Sidorenko's conjecture too, which means, yeah. So this means when t is large, then your blow up of star has a good lower bound, like this. But this t being large is necessary because we don't really have a good tool. But people really do believe that we could we should be able to reach this point like within 100 years. I don't know. Yeah. And this result here also kind of reminiscent of these Kvari-Schoch-Turan type results. Yeah. So we managed to prove that this large blow-up is Sidorenko because somehow large blow-up is good for lower bound. But if we are good at math, then someday we could do something better. Like, yeah, proving all the p's 1 would would prove the full conjecture. So, okay, so how much time? Half an hour left.
So how big is P then?
Oh, yeah, that's also a very good question. So we managed to prove something like this. Okay, so should I? Yeah, let me just squeeze in. Yeah, so for the remaining like 20 minutes, let me just sketch the proof of this theorem. So the story is as follows. So these other approaches also had some interesting remark. So let me just start with, so this other approach gave another alternative proof for even cycles being Sidorenko with a totally different Ramsey-theoretic approach using local denseness condition. I also talked about these type of things before, but let me just assume this as a black box. And we also wondered if the same kind of approach, so by assuming this, we also wondered we could obtain some more graphs, some other graphs, obtain some other Sidorenko graphs, sorry. So, and we managed to find something, but at the time we didn't really know how to push that further into these kind of ideas. So this is as follows. So if suppose I have, so this is just a fact. The sixth cycle is Sidorenko. It's just simple fact. You can show it yourself, or yeah, there are like 3 or 4 different proofs for this. And if I look at, so suppose I've blown up one part of C6, then the graph would look like this. Yeah. So this is say all the parts here are S vertices, and they are all connected to this vertex. And you can also easily prove that this graph H is Sidorenko. This is also not very hard. And the funny remark here is once you've done this, then you could blow up things asymmetrically, which means you can blow up these S1, S2, S3. So perhaps something is larger than S and something's smaller than S, and their average is just S. And you can prove that this new graph, say H prime, is Sidorenko. And this is where the Holder inequality comes in. So let me show you the proof. So to this end, I have to rewrite this inequality. So let me just rewrite this first. The H of G is the expectation of the x, y, s, y, z, s, z, x, ds. So let me just explain the notation. So dxy means the normalized number of the co-neighbors of x and y, the chosen vertices x and y. So if I fix these vertices x, y, and z, then the number of h that extends that partial embedding is exactly dxy to the s, dy yz to the s, and dzx to the s. Because I could pick these s vertices within these co-neighbors. So this is the, am I too fast? Does it make sense? Yes. Yeah. So this is the expression. And what I'm going to do is to apply the Erdős inequality on this function here. So let me just write the pH prime of G in the same way. S1, S2, This is again just the same rewriting. So far nothing happened. Yeah. And what I'm going to do is to permute these variables, x, y, and z. So I can just relabel these x, y, and z in the following way. There's no harm in relabeling things. So I can, for example, do this. Yeah. So far I've done nothing. Yeah. And yeah, I can do another round. And what I'm going to do is to apply Erdős inequality with these three expressions. Where's the eraser? So, recall that Erdős inequality gives you this is the Erdős inequality. Yeah. When f, g, and h are positive. Yeah. So what I'm going to do is to put these guys on the right-hand side, and yeah, by mixing these three up, I could get these ones. And yeah, it works because this FGH is the geometric mean of these three functions, right? And if I take the product of these three functions inside the integral, then what do I have? So for the xy, I have S1 here, and S3 here, and S2 here. So if I take all the product of all the 9 functions in here, then I'll get dxy to the S1 plus S2 plus S3. And hence, I basically have this cubed is at least, no, this cubed, not this cubed, because I have 1/3 power on the top. So this exactly tells you this inequality. And because this h is Sidorenko, I'm done. So one funny point is we actually knew this work this technique works for this asymmetric blow for C6 or other symmetric graphs, but we didn't really know how to use this idea to to derive such a theorem. So how to generalize this is basically do the same thing. Basically, so let me just, I can write my th of g. So forget about this h, and my h is just general bipartite graphs from here. So then I can write this function as follows, as a generalization of these rewritings over here. So this would be some function, say rho of x in B for B in B, which means, so here xn of B is the randomly chosen vertices for the vertices in the neighbor set of B. Like here x and y, yeah, like this is generalization of this dxy over here. So we basically look at one vertex over here and look at its neighbor. And because we are going to choose the vertex B amongst its co-neighbor, we can write this th of g like this. So here rho of xi is, so here xi means xi in I. So this is a random vector, the bunch of randomly chosen vertices. And then that's the normalized number of co-neighbors of xi I. So I can basically write this homomorphism density in terms of some product of functions. And as I've done here, what I've done here is to permute these three vertices. As I've done here, I just permute the variables in here and apply the Holder's inequality in the same way, and that gives you some inequality like this. But the thing is, it's not necessarily the graph that you know it's Sidorenko or not. So if I do this generalization of Holder trick, then you end up with some graph J. Well, J is not necessarily graph. Yeah, so here I lied a little bit. So J is not necessarily graph because it might end up with some rational powers over here. And because of that part, we need some large blow-up and divisibility conditions for the general statement. So, yeah. So here I lied a little bit, but there exists J such that you have such an inequality. And if I know that J is Sidorenko, so if J is Sidorenko, then we're done. So, yeah, firstly, it's important to observe the Holder trick gives you some inequality, and the second part is to prove that the lower bound graph is actually Sidorenko. And for that part, we need these reflection graphs and these algebraic Cauchy-Schwarz. Yeah. So, yeah. let me just, rather than proving something, let me just give an example of this argument. So one very infamous example that no one knows if it's Sidorenko or not is the Mobius strip, which means, so it's still unknown whether this H, let's say M, K5 minus a Hamiltonian cycle is Sidorenko. This is still open. So this is nothing but a graph with 10 vertices and 15 edges, which is pretty much frustrating. But if you do this trick on the square of this graph, so here I just take square because this is a vertex transitive graph. So I don't care which side I'm gluing along. So we can prove that the square of this graph is Sidorenko. So this is our result. And the proof can be sketched as follows. So if I apply this Holder trick, then to M square, then I end up with some graph, which means you have 5 vertices, and you put one vertex for every triple. Yeah. So how many vertices you have? This is 5 choose 3, so exactly 10 vertices on the other side. So this is what F53 means. So you basically build an incidence graph of every triple in a 5 vertex set. So
The Sidorenko conjecture is for bipartite?
yes. Yes.
So that's good difference here. So you take the one side and copy it.
Yeah. So
This
this
Yeah,
square. Yeah. But I didn't really specify the bipartition side because it's vertex transitive and hence no difference. Yeah. So, and this graph is Sidorenko because it's a reflection graph. How many? Yeah. So this is more or less the proof. But to manage some general graphs that possibly have different degrees on one side, we should blow up H in a possibly like a huge number, like A factorial. So we ended up with a statement like that. But for this particular graph, the M square really does work. So yeah, for a long time I suspected this graph wouldn't be Sidorenko, but now I have no idea. If it's square is Sidorenko. Yeah, actually, I mean, yeah, almost all of these colleagues believe that the conjecture should be false, I think. But these recent results made us a little bit skeptical about our old belief. Now I would say neutral, probably. Yeah, probably David still believes that it's false. I don't know. We haven't really, yeah.
And why is that graph important? Is that the smallest graph that's not known to be Sidorenko?
Well, it's vertex edge transitive and a Cayley graph. And well, if I delete an edge from this graph, then I'm not so sure it's Sidorenko or not. So I'm not 100% sure that it's a minimal graph that's unknown to be Sidorenko or not, but yeah. But this graph got famous because Sidorenko himself mentioned that this graph may be interesting, and since then many people tried, but well, we still have no idea how to prove that or disprove it. Yeah, and even we don't really know this graph satisfies this strictly stronger property like weakly norming thing or something like that. Yeah, so this is really a notorious one. Right, so I'm going to stop here.